Experimental organic chemistry. Refers to the second edition. The appearance of the second edition of the author textbook of organic chemistry made it advisable to prepare a revision of this laboratory guide in order that the references given to the text should refer to the new edition of the letter. Chapter 1. Laboratory methods. General directions to the student. Before beginning an experiment, read throughout to the end the directions which are to be followed. Many mistakes which involve additional work can be prevented by understanding beforehand just what is to be done. The import of the experiment should be clear, and the chemical reactions involved at each step should be understood before the work is started. References are given in each experiment to the section in the author textbook. The principle of organic chemistry, in which the chemical reaction involved are discussed. These references are given in boldface type. Those references to paragraphs in this book are indicated as 64, page 42. Keep a clear and concise record of the laboratory work. The notes should be written as soon as the experiment has been performed, and care should be taken to have the original record made during the course of the experiment of such a character that it serves as a permanent record of the work. Notes should not be taken on loose pieces of paper and afterward written out in the notebook. They should be written carefully in good English and should state briefly what was done and what was observed. It is necessary for the student to recognize what the experiment is to teach, why he was asked to do it. If the work consists in the preparation of some compound details for which are given in the laboratory guide, it is not advisable to take time to copy these details in the notebook. References to the pages in the book where the preparation is described should be given, and a statement made of the amounts of the substances used. If any unexpected difficulties arose, or if any improvement in the way of carrying out the preparation was used, these facts should be noted. Write equations for reaction taking place in the experiment and record the yield of the compound obtained. The substance should be put in a clean, dry glass stoppered bottle of appropriate size and be labeled. The student's name, the name, weight, and the boiling point or melting point of the substance should be recorded on the label. The boiling point or melting point should be that observed by the student for the sample itself, not the points recorded in the book. The student should use reasonable care in these manipulations. He should endeavor to get as large a yield as possible of the product sought, but should use judgment as to whether it is advisable to spend large amount of time to increase by a small amount the yield of the product. The process should not be carried out in the manner used with a quantitative analysis, a few drops may be lost here and there if they form but a very small portion of the total amount formed, and their recovery entails the expenditure of much extra time. It is not meant by this that the student be careless. We should develop the judgment as to relative value of a slightly higher yield of product and the time required to obtain it. Calculation of yield. The student should calculate in each preparation the percentage yield obtained. From the chemical equation for the reaction can be calculated the so-called theoretical yield. The percentage of this obtained is called the percentage yield. The latter is never equal to 100% for many reasons. It is often advisable to use an excess over the theoretical amount of one of these substances used in the preparation. The student should, before calculating the percentage yield obtained, determine whether an excess of one reagent has been employed. When one substance used in a preparation is much more expensive than the rest, it is customary to take the substance in such amounts that the largest yield possible calculated from the more expensive substance is obtained. For example, preparations involve the use of iodine are so carried out that the largest amount of the halogen possible is obtained in the substance prepared. In this case, the test of the skill with which the preparation is carried out is determined by the fact that the percentage yield should be calculated accordingly from the weight of iodine used. Integrity in laboratory work. The student should record in his notebook his own observation only, and the result he has obtained himself, unless there is definite statement to the contrary. If a student has carried out an experiment along with another student, a statement to this effect should be put into the notes. Caution in regard to laboratory work. A student uses in laboratory work in organic chemistry inflammable liquids and substances like sodium and phosphorus, which have to handle with great care. Unless care is exercised, fires may happen. The laboratory should be provided with a bucket of sand and a fire extinguisher. A heavy woolen blanket should be near at hand to be used in case the clothing catches fire. Inflammable liquids such as ether, alcohol, and benzene should not be poured into the jars provided for acids. Only liquid solutions should be extracted with ether, and the process should be carried out at least 12 feet from a flame. When carrying out a reaction in a test tube, care should be taken to hold the tube in such a position that if the contents are violently thrown out, they will not come in contact with the experimenter or any one in the neighborhood. If the odor of a substance in the tube is to be noted, do not look down into the tube. If this is done and a violent reaction takes place suddenly, the material in the tube may be thrown into the eye. When an organic compound has been prepared, it must be purified from the byproducts which are formed at the same time. In the case of solid substances, crystallization is ordinarily used for this purpose, although with a certain compounds purification can be more readily effected by sublimation or distillation processes, which are described below. Choice of solvent. The separation of two substances by means of crystallization is based on the fact that they are present in the mixture to be separated into its constituents in different amounts or on the fact that the two substances possesses different solubilities in the liquid used as a solvent. When it is desired to purify a substance by crystallization, a solvent should be selected, if possible, in which the impurity is readily soluble, and in which the substance sought is more or less difficulty soluble. Purification is effected most easily when the substance to be purified is appreciably soluble in the hot solvent and much less soluble in it when cold. If the two conditions stated above can be combined, and this is possible in many cases, purification is really accomplished. The solvents most commonly used in crystallization are water, alcohol, ether, benzene, petroleum, ether, dichlorine, carbon, bisulfide, chloroform, acetone, and glacial acetic acid. In certain cases, hydrochloric acid, carbon tetrachloride, ethyl acetate, toluene, and nitrobenzene have been found of particular value as solvents. In order to crystallize a compound, the solubility of which is not known, preliminary tests should be made with the solvents enumerated above, about 0.1 gram or less of the substance should be used in each test. The solid is placed in a small test tube and the solvent is added a drop at a time, and the tube is shaken after the addition of about 1 centiliter of the liquid. If the substance has not dissolved, the tube should be heated until the liquid boils. If the substance does not dissolve, more liquid should be added in small quantities until solution occurs. If a very large amount of the liquid is required for solution, or the substance proves insoluble, another solvent must be used. When a solution takes place, the tube is cooled by running water. If the substance separates, it is redissolved by heating, and the contents set aside to cool slowly when crystals will probably form. If the substance does not separate to a considerable degree when the hot solution is cooled, a similar test should be made with other liquids. If none of the solvents can be used in the way heater, the substance must be obtained by spontaneous evaporation, or a mixture of liquids must be used, a method described below. If the compound is to be crystallized by spontaneous evaporation, cold saturated solutions prepared by dissolving about 0.1 gram or less of the substance in a number of solvents are poured onto watch glasses and left to evaporate slowly. Some substances from solution from which the first crystals separate with difficulty. In such cases, the solution is seeded by adding a trace of the solid substance. A piece the size of the bead of a small pin is sufficient. Crystallization of such substances can often be brought about by scratching with a glass rod the side of the vessel containing the solution. The rough surface formed assists materially in the formation of the first crystal, after which crystallization proceeds readily. The liquid finally selected for the solvent should be on which yields well-formed crystals and does not evaporate too slowly. Use of frozen mixtures in crystallization. It often happens that substances which do not separate from their hot solution when the latter are cooled with water crystallize out well when the solutions are allowed to stand for some time in a freezing mixture. For this purpose, a mixture consisting of equal weights of sodium chloride and finely divided ice or snow is commonly used with snow, a temperature of Under 17 degrees is obtained. A mixture of equal weights of crystallized calcium chloride and snow gives the temperature. Under 48 degrees, a convenient freezing mixture is made by covering finely divided ice with commercial concentrated hydrochloric acid. Preparation of crystals. When a satisfactory solvent has been selected, the material to be crystallized is placed in a beaker and covered with the liquid. The mixture is heated to boiling over a free flame or on a steam bath. If the solvent used in the flammable, it is essential to avoid the presence of a free flame when alcohol, benzene, ether, or petroleum ether are used as solvents. The beaker is covered with a watch glass and the solvent is added in a small portion at a time until the substance is to be crystallized as passed into solution. It may happen that a small amount of a difficulty soluble impurity is present. In this case, it is not advisable to add enough solvent to dissolve the impurity. When the substance to be crystallized has been dissolved, the solution is filtered while not throughout a fluted filter paper into a beaker. Crystallizing dishes should not be used. If the substance crystallizes out during the filtration, either a hot water funnel can be used or enough of the solvent can be added to prevent crystallization. In the latter case, and whenever an excess of solvent has been used, it is advisable to concentrate the solution to crystallization after filtration. The solution is evaporated crystallization by boiling it gently. Tests are made from time to time to determine whether crystals will form when the solution cools. This can be done by placing a glass rod in the hot solution and then withdrawing it. If crystals appear when the drop of the liquid which adheres to the rod cools, the solution should be set aside and covered with a watch glass or filter paper. If crystals are not formed, the evaporation should be carried further. A hot water funnel is at time very useful if crystals form during the filtration. It consists of a funnel surrounded by a metal jacket in which is placed water that can be heated to its boiling point by means of a Bunsen burner. When inflammable liquids are used as solvents, the water should be heated and the burner extinguished before filtration. Disregard of this precaution has frequently led to fires. It is advisable to cut off the steams of the funnels to be used in the preparation of organic compounds. This eliminates the clogging of the funnel as a result of crystallization of solid in the steam. It also makes it unnecessary in most cases to use filter stands, as the funnel can be supported by the beaker, which is to hold the filtrate. If the beaker is too large for this, the funnel can be supported on a clay triangle placed on the beaker. The arrangement represented in Figure 1 is especially convenient for filtering solutions which deposit crystals of cooling slightly. During filtration, the beaker is heated on the steam bath or over a flame. The vapor which rises hits the funnel. The latter should be covered during filtration with a watch glass to prevent loss of heat from the liquid that it contains. The use of a mixture of two liquids as a solvent in crystallization. It is advisable to use as a solvent in purifying a substance a liquid in which a substance is readily soluble when heated and difficulty soluble in the cold. If such a solvent cannot be found, a mixture of two miscible liquids is often used, one in which the substance is readily soluble and one in which it is insoluble or difficulty soluble in crystallizing a substance. In this way, it is first treated with the hot liquid which dissolves it into the solution, is then added the second liquid, also hot, until the mixture begins to cloud. A little of the solvent is added to clear up the solution, which is then covered to prevent too rapid evaporation, and the mixture is set aside to crystallize. Pairs of liquids which are available for crystallization in this way are alcohol and water, alcohol and benzene, petroleum, ether and benzene, and alcohol and carbon disulfide. Separation of crystals. The separation of crystals from the mother liquor is effected by filtration under diminished pressure. A funnel is attached to a filter bottle by means of a rubber stopper. A perforated plate about 4 centimeters in diameter is placed in the funnel and covered with a circular piece of filter paper, the diameter of which is about 6 millimeters, greater than that of the plate. This paper is moistened with the solvent, the bottle is connected with the suction pump, and the air is drawn through the apparatus. The paper is fitted into place so that it covers the joint between the filter plate and funnel. If a crust has formed around the beaker on the surface of the liquid from which the crystals to be separated have formed, it should be carefully removed, as it will probably contain some of the impurities present. The remaining solution and crystals are then poured into the funnel and the suction applied. When all the liquid has been drawn off, the solid should be pressed down tightly with a spatula. The connection with the pump is broken and the solid of the funnel is moistened with some of the pure solvent used for crystallization. The crystals are followed to absorb the solvent and stay in contact with it for about half a minute. The suction is then applied and the crystals drain as fully as possible from the liquid. The filter bottle is again disconnected from the pump and the crystals covered again with the solvent and washed as before. Crystals should never be washed by pouring the solvent over them while the filter bottle is connected with the pump. If this is done, a large amount of liquid is required to wash the crystals, and there is great loss due to the solution of the crystals in the solvent. When the crystals have been freed by suction as much as possible from the liquid used to wash them, they should be removed to a porous plate and allowed to dry spontaneously in the air. In the preparation of many compounds, tertiary substances are often obtained along with the compound desired. In this case, the crystals first obtained from solution are often mixed with these substances. The tar may be removed by pressing the crystals on a porous plate and allowing them to stand undisturbed for some time. The residue from which the tar has been largely removed as a result of absorption into the porous plate is transferred to a clean part of the plate and is moistened with the solvent. The substance is left until the solution of the tarry product clinging to the crystals is absorbed. A second crystallization and the treatment with the porous plate generally yields a pure compound. When the crystals are thoroughly dry, a melting point determination should be made. If this is not sharp, the substance should be recrystallized. Decoloration of solution. If a substance contains tertiary materials which impart to it color, it can be purified usually by boiling a solution of it for some time with bone black and filtering the hot solution. The efficiency of the process and the amount of the bone black required are markedly affected by the quality of the latter. As an approximation of about 1 gram should be used for a solution of 215 centiliters, which is moderately colored. Liquids are purified by distillation. The form of apparatus ordinarily used is represented in Figure 2 in setting up the apparatus. The details noted below should be considered. The distilling flask should be supported by a clamp placed above the side arm, and the condenser by a clamp placed at its middle point. The side arm of the distilling flask should extend from about 1/2 its length into the inner tube of the condenser. Preparation of corks. Before being used, corks should be softened. This can be done by means of a press, which is made for this purpose, or the cork can be rolled on the desk while it is being processed firmly by means of a block of wood. It is in most cases not advisable to use rubber stoppers, as they may be attacked by the vapor of the liquid during distillation. Sharp cork boards should be used to make the holes of such a size that the tubes to pass throughout fit snugly. In boring corks, it is advisable first to push the bore with a rotary motion halfway through the cork, taking care that the hole is bored throughout the center of the cork. The bore is then removed, and the hole made from the center of the other end of the cork to meet that first made. By proceeding in this way, the edges of the holes on the two sides of the cork will be clean cut, and thus make a tight joint with the tube to be passed throughout the hole, and the latter will run evenly throughout the axis of the cork. Position of the thermometer. The bulb of the thermometer should be so placed that it is about 1 inch below the side arm of the distilling flask. If the liquid boils at such a point that the end of the thread of mercury is hidden by the cork during the boiling, the position of the thermometer can be shifted downward, or the upper or lower end of the cork can be cut away. The bulb should never be placed above the sidearm, since it is essential that it be covered completely by the vapor during the distillation. Heating the flask. The best way of heating the distilling flask is determined by the boiling point of the liquid to be distilled. If the liquid has a low boiling point up to about 18° or 19°, the flask should be placed in a water bath in such a position that the level of the water is just below that of the liquid in the flask. Toward the end of the distillation, the flask should be raised in order to prevent superheating the vapor of the liquid. With very volatile liquids, great care is necessary to prevent this superheating. Another method, which is often used, is to place the flask on an abscess border, in which a hole is bored having a diameter about 1/2 that of the flask. The smallest flame which will furnish heat enough to boil the liquid is used. This method can be used for distilling in general, whatever the boiling point of the liquid. In a flask of 215 capacity or greater is used, it is advisable to support it on a wire gauze. This precaution is also advisable when the burner is to put in place and the distillation allowed to take place of itself. It is often better to hold the burner in the hand and keep the flame in motion during the distillation. In this way, the process is more carefully watched and the rate of distilling can be controlled. The heating of the flask should be discontinued before all of the liquid has distilled. It is customary to leave a residue of 2 to 5 centiliters in the flask. Rate of distillation. The distilling flask should be heated in such a way that the distillate falls in drops from the end of the condenser at the rate of about 1 drop per second. Care should be taken to avoid the rapid distillation of very volatile flammable liquids such as heater, alcohol, and carbon disulfide. If such liquids are distilled very rapidly, a part of the vapor is not condensed and the fire may result when this vapor comes in contact with a nearby flame. In order to prevent accident, the method of collecting such liquid, which is described in 34 page 23, should be used. Distillation of high boiling liquids. When a liquid boils above 115 and a air condenser should be used instead of the kind shown in figure 2, which is supplied with a water jacket. If one of the latter type is used, the inner tube, cooled by running water, is apt to crack when vapor of the high boiling liquid comes in contact with it. The inner tube without jacket is used as an air condenser. When a substance which boils at a high temperature above 1300 and solidifies readily is distilled, it is customary to use no condenser but to collect distillate directly at the end of the side arm of the distilling flask. If in this case, or when an air condenser is used, the distillate solidifies before it reaches the receiver, the tube should be gently heated by passing the flame of a burner slowly along its length. It is necessary to prevent the filling of the side arm of the flask with solid. If this occurs and the boiling is continued, the vapor produced soon reaches a sufficient pressure to cause an explosion. When this method is unsatisfactory on account of the high melting point of the substance, it is advisable to distill from a retort. On account of the large diameter of the neck of the retort, a considerable quantity of the solid can be collected in it. Before the solid fills the neck at any point, the distillation is stopped. The neck of the retort is heated and the liquid collected in a beaker. This distillation is then continued. Fractional distillation. When it is necessary to separate 2 or more liquids by the distillation, special forms of distillating flasks should be used. These are so constructed that they decrease materially the time required to effect the separation. This is accomplished by subjecting the vapor the gradual cooling before it is finally condensed. In this way, the less volatile constituents of the vapor are condensed and returned to the flask, while the more volatile parts pass on through the condenser. The types of flasks used are illustrated in figure 3, 4, and 5. The arrangement represented in figure 5 is very efficient, especially when a small amount of a liquid is to be fractioned. After the liquid has been placed in the flask, a number of glass beads tied together with a cotton thread are supported by the thread, and the neck of the flask is filled to the place indicated in the diagram with glass beads. The more complicated arrangements are supplied as tubes which are fitted by a cork to a round bottom flask. Figure 6, 7, 8, and 9 illustrate the forms commonly used. The most efficient form is that of ample, figure 9, which consists of a tube filled with glass beads. The least efficient form is that of Wurtz. The efficiency of the label Henninger tube and that of the Linsky tube lie between the two extremes stated. Another simple form of apparatus for fractioning low boiling liquids, which is especially valuable when small quantities only are available, can be constructed from a glass flask and a test tube in the way illustrated. The cold water enters throughout the long tube in the test tube and passes upward. Regulating the flow of water, the cooling effect on the vapor can be varied. The principle of fractional condensation, which is used, affects the separation of the vapor into low and high boiling constituents. The combination of a still air of this type with a column containing short pieces of glass tubing about 15 mm long and 3 mm internal diameter makes perhaps the most efficient fractioning apparatus available for laboratory use. It is illustrated in figure 11. When a mixture of two liquids which boil at a different temperature is distilled, the temperature of the vapor during the distillation rises in most cases from the boiling point of one of the liquids to that of the other. The distillate, which is collected, first contains a large proportion of the lower boiling liquid, while that collected toward the end of the operation is rich in the higher boiling liquid. In order to separate the two, the mixture is subjected to what is called fractional distillation. The process is carried out in the following way. The mixture is distilled slowly, and the receiver in which the distillate is collected is changed from time to time as the boiling point of the liquid rises. In this way, the mixture is separated into what are called fractions. The number of fractions collected and the limits of the boiling point of the various fractions are determined by the difficulty of separating the mixture and the purity of the products desired. The lowest boiling fraction is next placed in a clean flask and distilled. When the temperature reaches that of the upper limit of the fraction, the heating is stopped and the second fraction added to the flask. Distillation is then continued until the upper limit of this fraction is reached, the distillate being collected in the appropriate receiver. The process is continued in this way until all the fractions have been distilled a second time. It will be found as a result of this fractionation that the distribution of the liquid in the several fractions is different from that obtained the first time. The fractions which boil at temperatures near those of the boiling points of the constituents of the mixture increase in volume. By repeating the process a sufficient number of times, practically all of the liquid can be separated into its constituents. In the following table are given the results of the fractional distillation of a mixture of 15 centiliters of methyl alcohol and 15 centiliters of water. The volumes of the fractions obtained after each of 6 fractions are recorded. When the liquids form a constant boiling mixture, they can not be separated in pure condition. By fractional distillation, the boiling point of a mixture of ethyl alcohol and water which contains 96% by weight of the former is lower than that of pure alcohol. As a consequence, when a mixture of the two substances is subjected to repeated fractional distillation, the constant boiling mixture is obtained. In order to prepare pure alcohol, it is necessary to remove the water from the mixtures by chemical means. Very few cases of this kind are met with in the purification of organic compounds. Many substances which decompose when distilled at atmospheric pressure distill without decomposing when the pressure is reduced. This results from the fact that the temperature at which a substance boils is markedly affected by the pressure. For example, benzophenone boils at 306 degrees at 1716 mm pressure and at 117 degrees at 15 millimeters. Pressure. The effect of change in pressure on the boiling point increases rapidly as the pressure decreases. Steric acid, for example, boils at 291 degrees at 100 millimeters, at 232 degrees at 15 millimeters, and 155 degrees under the best vacuum obtainable with a mercury pump. A difference of 18 millimeters in pressure from 100 millimeters to 15 millimeters causes a change in boiling point of 15 and 19 degrees, whereas a difference of 15 millimeters from 15 millimeters to 0 millimeters lowers the boiling point 70 degrees. Many substances which distill with partial decomposition at atmospheric pressure with a good water pump, a convenient arrangement of the apparatus required for distillation under diminished pressure is present by figure 12. A piece of glass to be drawn out to a fine opening is attached to the right arm of the manometer and indicated in the figure. This prevents the mercury from being forced out of the tube when the cork is opened to admit air after the distillation has been completed. The flask to contain the substance to be distilled is fitted with the thermometer and the tube, which is drawn out to a fine opening at one end. To the other end, the tube is attached a piece of rubber tubing carrying a screw clamp. This tube is provided to prevent violent bumping during the distillation. By regulating the screw clamp of the apparatus has been attached to the vacuum pump, a rapid stream of air bubbles can be drawn throughout the liquid. As the latter is heated, the vapor formed passes into the bubbles, and superheating and the consequent bumping are largely avoided. The position of the tube is so adjusted that the fine opening almost touches the bottom of the flask. It is often advisable to replace the plain distilling flask like the one shown in this picture by one of the glassine type. With the latter is used by pumping aqueous, the material in the flask is not so apt to be forced over into the condenser. Other modifications of the form of the tube to admit air into the flask are often used. If the neck of the flask is small and it is impossible to insert into it both the thermometer and a glass tube of the ordinary diameter, the part of the tube which is to pass throughout the cork is drawn out to a capillary and is inserted throughout a small hole made with a stout needle or the end of a file. One end of the tube is left with such a diameter that the rubber tubing and the screw clamp can be attached to it. A second modification is often used on account of its convenience is illustrated there. A straight glass tube is selected of such a diameter that the thermometer passes into it easily. The tube is drawn out at one end at a small opening. It is then cut off at the other end at such a point that when the thermometer is placed in it and it is put into the flask, the bulb of the thermometer is in the correct position with regard to the side arm of the flask. A piece of rubber tubing provided with a screw clamp is attached to the upper end of the tube. When liquids which boil at a very high temperature are distilled, it is customary not to use an air condenser but to connect the receiver directly with the side arm of the flask which contains the liquid to be distilled. In assembling the distilling apparatus, a rubber stopper may be used to attach the receiver to the condenser, provided care is taken to prevent the hot liquid from coming in contact with the rubber. Great care should be exercised in selecting the cork to be used. It should be as free as possible from holes after the apparatus has been set up. Small leaks often be caused by connecting the cork with collodion. A convenient arrangement of the manometer and the connections between the pump and the receiver is represented there. A number of forms of manometers are used to register the pressure inside the apparatus. A simple form, which can be readily made from a supply of mercury, a metal stick, and a piece of glass to be illustrated in the figure. In order to determine the pressure in the apparatus, the reading of the scale opposite the level of the mercury is the manometer are subtracted, and this difference is subtracted from the height of the barometer. It is necessary to insert an empty bottle between the pump and the receiver. When the apparatus has been evacuated, water may run back from the pump into the receiver as a result of a slight change in the pressure of the water caused by the opening of a cock in the neighborhood. The inserted bottle serves as a trap to catch this water. At sea is a top cock throughout, which air can be let into the apparatus. This is of value at the end of distillation or in case the boiling liquid begins to froth or bump violently. In later case, letting in a little air prevents the ejection of part of the contents of the flask into the receiver. Method of distillation. Before introducing the liquid to be distilled, the whole apparatus should be tested. The screw clamp B should be closed and the receiver connected by a heavy walled tube to the pump. In no part of the apparatus should rubber tubing be used which collapse under diminished pressure. If no heavy tubing is available, the connection can be made with glass tubing joined by ordinary rubber tubing. The ends of the glass tubes being brought together so that the connection rubber tubes cannot collapse. When the apparatus has been connected with the pump, the pressure should be reduced to about 20 mm. If this cannot be done, either the pump is a pure one or the apparatus has not been well put together. The cause can be determined as follows. First, test the pump by connecting it directly with the manometer, making sure that there is not a leak in the connection tubes. Second, disconnect the tube at D and close it with a pinch, cork or glass rod. If the reduction is in pressure insufficient, will show that all the connections from the pump up to this point are tight. Next, disconnect the flask from the condenser and connect it by means of the sidearm to the pump and the manometer. This will determine whether the cork provided with the thermometer and the tube to admit air is tight. It is probable that the leak will be found at this point. If everything is tight, connect the flask with the condenser and the lower end of the latter with the pump. This will test the tightness of the joint between the flask and the condenser. The apparatus is next completely adjusted and tested again when, if no leak has been discovered up to this point and the pressure cannot be sufficiently reduced, it is evident that the connection between that condenser and receiver is a fault. When the apparatus has been found to be tight, the product to be distilled is introduced into the flask, which should be filled to not more than one-half its capacity. The suction is applied and the screw clamp B opened very slowly so that a stream of air bubbles pass through the liquid. The flask is heated by a bath containing oil or preferably a low melting alloy such as roses or wood metal. It is often better to heat the flask by means
of a free flame as the amount of heat applied can be quickly regulated. When a free flame is used, it should be kept in constant motion, and the surface of the liquid where it comes in contact with the flask should be heated rather than the bottom of the flask. This can be done by moving the flame around the flask and letting it come in contact with the latter to the side and not the bottom. If frothing suddenly begins and there is a chance of the contents of the flask rushing over into the receiver, such a result can be prevented by opening the cork, which admits air to the apparatus. Special forms of apparatus have been divided to fractionate a liquid by distillation under diminished pressure. It is often simple to use the apparatus described above and change the receiver when the limits of the fraction have been reached. Substances which are practically immiscible with water and have an appreciable vapor pressure at 100 degrees can be readily separated from those which have a very small vapor pressure at this temperature but pass steam throughout the mixture, the process which is of special value in separating organic compounds from tire materials formed in their preparation is carried out in apparatus arranged as represented in that figure. The flask A is connected with a supply of steam. This can be conveniently generated in a kerosene can, which is supplied with a long glass tube reaching to the bottom of the can to act as a safety valve. Into the flask is put the substance to be distilled. The flask should be set up at an angle as indicated in the diagram. By placing the flask is this position any of liquid which is violently thrown up against the flask as the result of the inrush of steam will not be forced throughout the condenser into the receiver. The tube throughout which the steam is led should be so bend that its end almost touches the lowest point of the flask in its inclined position. By the means and steam it forced throughout the heavy liquid to be distilled, which is consequently kept in motion. If the liquid is not stirred up by the incoming steam, distillation takes place very slowly. The vapor issuing from the flask consists of a mixture of steam and the volatile substance to be distilled. When this condenses, two layers are formed. The theory of the process is briefly as follows. When a mixture of two immiscible liquids is heated, each substance vaporizes independently of the other. When the sum of the vapor pressure of two liquids is equal to the pressure of the atmosphere, the mixture distills. The relation between the weight of the two substances obtained determined by their molecular weights and their vapor pressures at the temperature of distillation. The case of nitrobenzene and water is an example. When steam is passed into nitrobenzene, the mixture boils at 90 degree when the atmospheric pressure is 70-16 millimeters. At this temperature, the pressure of water vapor is 70-33 millimeters and of nitrobenzene 27 millimeters. Consequently, the relation between the weight of water and that of nitrobenzene is as 18 for 70 133 is to 173 per 27 per, or approximately 4 to 1. Although the vapor pressure of nitrobenzene is small at 99 degrees, its larger molecular weight compared with that of water leads to the result that about 1/5 of the product obtained by distilling with steam consists of nitrobenzene. When the vapor pressure of a compound is as low as 10 millimeters at 100 degrees, it can be advantageously distilled with steam. Orthonitrophenol can be conveniently separated from paranitrophenol on account of the fact that the former has an appreciable vapor pressure at 100 degrees and is consequently volatile with steam. 13. When the vapor pressure of a substance increases rapidly near 100, the rate at which it distilled can be measured increased by adding to the mixture of it and water a substance soluble in water. The latter increases the boiling point of the liquid by saturating the water with calcium chloride and mercury, rising the temperature at which distillation occurs can be affected, with the consequent increase in the vapor pressure of the organic compound undergoing distillation. When the vapor pressure of a substance is appreciable only at a temperature considerably above the boiling point of water, it may often be separated from less volatile compounds. By distillation, substance is heated in a oil bath and steam, which has been passed throughout a hot coil of copper, is conducted throughout it. By extraction is meant the process of removing from a mixture, usually an equal solution, one or more substances by shaking with a liquid in which the substances to be removed are soluble. Aniline, for example, is somewhat soluble in water. When the solution is shaken with the ether, a large part of the aniline is removed from the water and passes into solution in the ether, as aniline can be recovered much more readily from a ethereal solution than from an aqueous solution. Extraction of such solution is made use of it in the preparation of the compound. Liquid used for extracting must be immiscible with the solution to be extracted. Method of extraction. In extracting a solution, it is shaken in a separator funnel with a liquid in which the substance to be extracted is readily soluble. The substances commonly used for this purpose are ether, chloroform, benzene, petroleum ether, or lignin, and carbon disulfide. Ether is generally used as it is an excellent solvent for many organic compounds, and on account of its low boiling point, it can be readily removed. These disadvantages connected with the use of ether are its great inflammability and the fact that it is somewhat soluble in water and dissolves appreciable quantities of water. Water dissolves approximately 10% of its volume of ether. When large volumes of aqueous solution are extracted, there is a loss of ether, which is an expensive substance. With these losses decreased by saturating the solution to be extracted with sodium chloride. On account of the fact that ether dissolves about 2% of its volume of water, ether extracts have to be dried in most cases before the ether is removed by evaporation. The relation between the volume of an aqueous solution to be extracted and the volume of the solvent used for extraction is determined by the relative solubilities of the substances to be extracted in water and the solvent used. If an equal solution of a substance is extracted with ether, the amount of the substances found in the two liquids will be proportional to the solubilities in the two solvents and the amounts of the latter. If the substances is equal soluble in water and the ether and the volumes of the two liquids are the same after extraction of half of the substance will be found in ether. If the substance is twice as soluble in ether as in water, the relation of the amount present in the ether will be to the present in the water as 2 is to 1, that is 2/3 will be present in the ether and only 1/3 in the water. By shaking the aqueous solution with a second portion of ether, 2/3 of the substance present, that is 2/3 of 1/3, or 2/9 of the original amount, will be removed and 1/9 will remain dissolved in the water. After 3 extraction, but 1/27 of the substance will remain dissolved in the water. In the above example, a certain volume of solution was extracted 3 times, using each time a volume of ether equal to that of the aqueous solution. The result would have been different if the solution had been extracted with the 3 volumes of ether.